You stand on the surface of a planet that feels vast in a way that is difficult to fully articulate. The ground beneath you seems stable and unending. The horizon stretches outward in every direction. And no matter how far you travel, there is always more to see. Continents extend for thousands of miles. Oceans cover most of the surface. And even the highest mountains are only small features on something much larger. From a human perspective, Earth does not just appear large. It feels overwhelmingly expansive, almost beyond the limits of direct experience. For most of human history, this impression was not questioned. People understood the world through what they could observe. And everything they saw suggested that Earth was the entire stage of existence. The sky appeared as a dome overhead. The ground seemed flat and continuous, and the motions of the sun, moon, and stars reinforced the idea that everything revolved around this central surface. The curvature of the Earth is too subtle to detect from the ground, and without the ability to travel far or rise high above the surface, there was no obvious reason to imagine anything different. The conclusion that Earth was vast and perhaps all-encompassing was a natural result of limited perspective. Even now, with modern knowledge, the intuitive sense of Earth's size remains tied to experience rather than numbers. The planet has a diameter of about 8,000 miles and a surface area of roughly 197 million square miles. But these figures are abstract. What feels more concrete is the time and effort required to move across it. Traveling from one side of a country to another can take days. Crossing an ocean once required months or even years. Exploring every region of the planet is not something any single person could accomplish within a lifetime. If you consider the idea of visiting every square mile of Earth, even briefly, the scale becomes clearer in practical terms. Spending just 1 second in each location without stopping would take more than 6 years. This does not include the time needed to reach those places or understand them. Only the act of being present. The number of locations is simply too large for human timescales to comfortably grasp. A similar perspective appears when thinking about distance in terms of movement. The circumference of Earth at the equator is about 25. 0,0,0 miles. Walking that distance at a steady pace for several hours each day would take years to complete. This is not a complex journey, but a simple path around a single line on the surface. Yet even this limited task extends far beyond what most people would ever attempt. These examples highlight how the sense of Earth's size is closely linked to human limitations. Distance is often interpreted through effort, time, and accessibility. A place that cannot be easily reached begins to feel distant, and a surface that cannot be fully explored begins to feel vast. The planet becomes large not only because of its physical dimensions, but because of how those dimensions relate to human capability. This relationship between perception and scale has shaped how people understand their place in the world. When all observations are made from within the same environment, that environment naturally appears central and dominant. The ground feels fixed. The sky appears to move, and the surrounding space seems to extend indefinitely. These impressions are consistent and reliable within everyday experience, even if they do not represent the full structure of reality. What emerges from this is a form of scale that is relative rather than absolute. Earth is large in relation to human size, speed, and lifespan. It is large because it exceeds the boundaries of what can be easily measured through direct experience. The difficulty lies not in the numbers themselves, but in translating those numbers into something meaningful at a human level. The first meaningful change in perspective does not come from something overwhelmingly distant or abstract, but from the closest object beyond Earth itself, the moon. It is familiar, visible almost every night, and yet it represents the first step away from a purely Earth-centered sense of scale. Unlike distant stars, the moon feels connected to everyday experience. It rises and sets, changes shape through its phases, and appears large enough in the sky to seem comparable to other celestial objects. Because of this familiarity, it becomes a useful reference point for understanding how scale begins to shift when Earth is no longer the only frame of comparison. The moon orbits Earth at an average distance of about 384 kilometers, or roughly 238, 855 miles. At first glance, this number may not carry much intuitive meaning, but it can be translated into more familiar terms. That distance is equivalent to traveling around Earth's equator nearly 10 times. What seems like a short gap in the sky is, in reality, a vast separation when measured against human standards of distance and movement. Even with modern technology, reaching the moon is not trivial. The Apollo missions, traveling at speeds far beyond anything available in everyday transportation, still required about 3 days to complete the journey. This alone begins to introduce a new scale, one where distances are measured not just in kilometers, but in sustained motion over extended periods. In terms of size, the moon is not dramatically smaller than Earth. Its diameter is about 474 kilometers, which is roughly 27% of Earth's diameter. This means that visually and structurally, it is still a substantial object. If Earth were represented as a basketball, the moon would be about the size of a tennis ball. This comparison preserves the sense that both bodies are significant, but it also introduces proportion. The moon is clearly smaller, yet not insignificant. It exists as a secondary object within a larger system, maintaining a relationship that is both gravitational and spatial. However, the most important aspect of the Earth-Moon system is not the size of the moon, but the distance between them. The separation between Earth and the moon is about 30 times the diameter of Earth itself. This creates a striking visualization. It would be possible to line up approximately 30 Earths side by side in the space between the two bodies. What appears as a close pairing in the night sky is, in reality, separated by an immense region of near total emptiness. This is often misrepresented in images where Earth and the moon are shown much closer together for clarity, but the actual scale reveals something different. The space between them is not filled with matter or intermediate objects. It is largely empty. This realization introduces an important concept, even in what might be considered a local cosmic environment. Space is not densely populated. The distances between objects are large compared to their sizes, and most of the volume is unoccupied. The Earth-Moon system, despite being one of the closest and most familiar relationships in astronomy, is dominated by empty space rather than physical substance. This challenges the intuitive expectation that objects in proximity should be closely packed, an expectation shaped by everyday experiences on Earth, where distances are small and environments are dense. At the same time, the moon plays a significant role in shaping conditions on Earth. Its gravitational influence produces tides, affecting oceans and coastlines in a regular, predictable cycle. It also contributes to the stability of Earth's axial tilt, which helps regulate long-term climate patterns. Without the moon, Earth's rotation could vary more dramatically over time, potentially leading to more extreme environmental conditions. This highlights that even across large distances, interactions remain important. Space may be mostly empty, but the forces that act across it are not negligible. Another detail that reinforces the interplay between size and distance is the apparent similarity between the moon and the sun when viewed from Earth. Both appear to occupy roughly the same size in the sky, allowing for total solar eclipses where the moon can completely cover the sun. This is not because they are similar in size, but because of a coincidence in scale. The sun is about 400 times larger than the moon, but also about 400 times farther away. This balance creates a visual alignment that would not occur if either distance or size were slightly different. The Earth-Moon system, when examined closely, marks the first clear departure from a purely human-centered perception of scale. It introduces distances that are large compared to Earth itself, reveals that space is mostly empty even at close range, and shows that size and separation must be considered together rather than independently. This shift does not yet make Earth seem small in an absolute sense, but it establishes a new framework in which size is no longer defined solely by direct experience. The shift that begins with the moon becomes far more pronounced when attention turns to the sun, because this is the point where comparisons stop feeling intuitive and start becoming overwhelming. Up to this stage, Earth still retains a sense of importance, not because it is objectively large, but because it has been the reference point for everything else. The moon is smaller, the distance is large, but Earth remains central in the comparison. That changes immediately when the sun is introduced, not as a distant light in the sky, but as an object with measurable size, mass, and physical dominance over the entire system. The sun has a diameter of about 39 million kilometers, or roughly 864, 0,0,0 miles. This makes it about 109 times wider than Earth. While that ratio alone is significant, it does not fully capture the difference in scale. Volume grows much faster than diameter. And when that is taken into account, the comparison becomes far more extreme. Approximately 3 million Earth-sized spheres could fit inside the sun. Every ocean, every mountain, every continent, and every structure ever built exists on a planet that occupies less than 1/1,000,000th of the sun's volume. The difference is no longer something that can be easily visualized through everyday experience. It requires accepting that the sun is not just larger, but vastly larger in a way that compresses Earth into a negligible fraction of the total mass. Reinforces this imbalance even further. The sun contains about 86% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid and comet combined accounts for only about 14%. This means that the gravitational structure of the solar system is almost entirely determined by the sun. Earth does not anchor the system in any meaningful sense. Instead, it follows a path defined by a much larger object, held in orbit by forces that operate on a scale far beyond anything experienced on the surface of the planet. Distance adds another layer to this shift in perspective. The average separation between Earth and the sun is about 150 million kilometers, or 93 million miles. This distance is defined as one astronomical unit, a standard measure used in astronomy because of its importance in describing planetary orbits. Light, traveling at approximately 300 kilometers per second, takes about 8 minutes and 20 seconds to make this journey. This introduces a delay between events and observation that does not exist at human scales. If the sun were to change in any way, that change would not be known on Earth immediately. Information itself requires time to travel across this distance. When translated into more familiar terms, the scale becomes clearer. A vehicle moving at typical highway speeds would require over 170 years to reach the sun. Assuming it could travel continuously in a straight line, even the fastest spacecraft ever built, moving at hundreds of thousands of miles per hour, still take months to approach it. The gap between Earth and the sun is not just large, it represents a different category of distance. One where conventional methods of travel become impractical and time spans extend beyond individual human lifetimes. The sun's physical processes further emphasize its scale. At its core, nuclear fusion converts approximately 600 million tons of hydrogen into helium every second. This process releases an enormous amount of energy, sustaining the light and heat that make life on Earth possible. The surface temperature of the sun is around 500 degrees Celsius, while the core reaches temperatures of about 15 million degrees Celsius. The pressure at the center is hundreds of billions of times greater than atmospheric pressure on Earth. These are conditions that do not merely exceed human experience, but exist entirely outside the range of environments that can be directly encountered or reproduced. Despite all of this, the sun is not considered exceptional on a cosmic scale. It is classified as a G-type main sequence star, often described as an average or typical star. It is neither among the largest nor the smallest, neither unusually hot nor unusually dim. This introduces an important implication. If the sun, with its immense size and energy output, is considered ordinary, then the framework of comparison extends far beyond the solar system itself. The introduction of the sun fundamentally alters the role of Earth within its own environment. Earth is no longer the dominant object in its immediate system, nor even a significant contributor to its overall mass or structure. It becomes one of several smaller bodies orbiting a much larger central source. The shift is not just numerical but conceptual. Earth transitions from being a primary reference point to a secondary object defined by its relationship to something far larger. The sense of scale that once made Earth feel vast begins to lose its foundation when placed alongside an object that exceeds it by such a large margin. Once the sun is taken as the dominant object, the rest of the solar system begins to fall into place not as a collection of equally significant bodies, but as a set of smaller objects distributed across an unexpectedly large and mostly empty region of space. The planets, which often feel like major landmarks when listed one after another, are in reality separated by distances so vast that their sizes become secondary to the space between them. What appears in diagrams as a compact system is, in physical terms, an extended structure where emptiness defines most of the volume. The inner solar system contains the rocky planets, Mercury, Venus, Earth, and Mars. These worlds orbit relatively close to the sun, all within about 1.5 astronomical units. On a simplified diagram, they appear clustered together. But even here, the distances are considerable. Mercury, the closest planet, orbits at an average distance of about 58 million kilometers from the sun, while Earth orbits at about 150 million kilometers. The gap between these orbits is not filled with anything substantial. It is a region of space where matter is sparse, and objects are separated by millions of kilometers of near total emptiness. Beyond Mars lies the asteroid belt, often imagined as a dense field of rocks and debris. In reality, it is another example of how misleading visual representations can be. The asteroid belt contains millions of objects, but the distances between them are so large that a spacecraft passing through would be unlikely to encounter even a single asteroid at close range. The total mass of all the material in the belt is less than a small fraction of Earth's mass. It is not a crowded region, but a wide zone populated by small bodies spread thinly across a vast volume. Moving outward, the scale increases dramatically with the gas giants. Jupiter, the largest planet in the solar system, has a diameter of about 143 kilometers, making it more than 11 times wider than Earth. In terms of volume, it could contain over 300 Earths. Its mass exceeds that of all the other planets combined, reinforcing its role as the second most dominant object after the Sun. Yet even Jupiter, despite its size, occupies only a tiny fraction of the space within its orbit. It circles the Sun at an average distance of about 5 astronomical units, meaning it is more than 5 times farther from the Sun than Earth is. And the region between Mars and Jupiter is largely empty. Saturn, Uranus, and Neptune extend this pattern further. Saturn's diameter is about 120 kilometers. And while it is less dense than Jupiter, it remains a massive object capable of containing hundreds of Earths. Uranus and Neptune, often referred to as ice giants, are smaller but still far larger than Earth, each with diameters roughly 4 times that of our planet. Their orbits lie at distances of about 19 and 30 astronomical units, respectively. By the time Neptune is reached, the scale of the solar system has expanded to a region where even light takes several hours to travel from the Sun. Despite the increasing distances, the same pattern persists. The planets themselves, no matter how large, occupy negligible portions of the space they move through. The dominant feature of the solar system is not the planets, but the emptiness between them. This becomes even more apparent beyond Neptune, where the Kuiper Belt extends outward as a broad region of icy bodies. Pluto, once considered a planet, is one of the larger objects in this region, with a diameter of about 377 kilometers. Much smaller than Earth, thousands of similar objects exist, but they are spread across billions of kilometers, forming a diffuse structure rather than a concentrated one. Far beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical distribution of icy objects that surrounds the solar system at distances reaching tens of thousands of astronomical units. This region represents the outer boundary of the Sun's gravitational influence. Yet it is so distant that its objects are only weakly bound to the Sun. The space between these objects is immense, and no direct observations have confirmed their presence individually. Their existence is inferred from the behavior of long-period comets that enter the inner solar system. When the solar system is viewed as a whole, a consistent pattern emerges. The Sun contains nearly all the mass. The planets are relatively small by comparison, and the vast majority of the system's volume is empty space. Even the largest planets are separated by distances that make direct interaction rare and infrequent. If the Sun were scaled down to the size of a basketball, Earth would be no larger than a small grain placed several meters away, and Neptune would lie far beyond. requiring a large open field to represent the full system. This perspective alters how the solar system is understood. It is not a compact arrangement of closely packed objects, but an extended structure defined by separation. The planets serve as markers within a much larger framework where distance, rather than size, becomes the defining characteristic when the boundary of the solar system is left behind. The change in scale is no longer gradual but immediate, because the distances between stars introduce a level of separation that cannot be compared to anything within planetary system. Inside the solar system, distances are measured in astronomical units, and travel times can still be expressed in months or years. Once attention shifts to the nearest stars, those units become insufficient, and a different measure is required. This is where the concept of the light year becomes necessary, not as a theoretical construct, but as a practical way to describe distances so large that conventional intuition fails. A light year is the distance light travels in 1 year, approximately 46 trillion kilometers. This unit reflects both distance and time because it directly links how far something is with how long it takes for information to travel from it to an observer. The nearest star system to the Sun, Proxima Centauri, is about 24 light years away. This means that the light reaching Earth from that star today began its journey more than 4 years ago. Even at the speed of light, which is the fastest possible speed in the universe, there is a measurable delay. This introduces a fundamental shift in how space is experienced, where observation always involves looking into the past. To understand the magnitude of this distance, it is useful to compare it with the scale of the solar system. The distance from Earth to the Sun is about 8 light minutes. Extending that to Proxima Centauri requires multiplying that distance by roughly 268. Lean. If the space between Earth and the Sun were reduced to a single unit, the distance to the nearest star would expand to a scale that is no longer easily visualized in familiar terms. The solar system, which already seemed large, becomes extremely small when placed within this broader context. Human technology further emphasizes this separation. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. After traveling for decades, it has reached a distance of about 15 billion miles from Earth, which is still only a small fraction of the distance to Proxima Centauri. At its current speed of approximately 17 kilometers per second, it would take more than 70,000 years to reach that star, assuming it were even traveling in the correct direction. This highlights a key point. Distances between stars are not just large, but effectively unreachable with current or foreseeable methods of travel. Even if hypothetical advancements allowed spacecraft to travel at a significant fraction of the speed of light, the time required to reach nearby stars would still span decades. A journey at 10% of the speed of light would take over 40 years to reach Proxima Centauri, not accounting for the additional challenges of acceleration, deceleration, and long-term survival. These timescales extend beyond typical human lifespans, introducing practical limitations that are not present within the solar system. Other nearby stars reinforce this pattern. Sirius, one of the brightest stars visible from Earth, is about 6 light years away. Betelgeuse, a prominent red supergiant, lies hundreds of light years distant. At these scales, Individual stars are separated by vast regions of space that contain very little matter. The density of objects decreases dramatically, and the average distance between stars becomes the defining feature of the environment. Space at this level is not crowded, but sparse, with stars acting as isolated points within a much larger volume. From this perspective, Earth undergoes another shift in significance. Within the solar system, it is one of several planets orbiting a dominant star. At the scale of interstellar space, even the solar system itself becomes difficult to distinguish. If observed from the distance of a nearby star, the sun would appear as a single point of light, and Earth would not be visible at all. Lost within the brightness of its host star, the entire planetary system would effectively disappear as a distinct structure. This leads to the concept of cosmic isolation. Each star system exists as a largely self-contained environment, separated from others by distances that limit interaction. While gravitational forces extend over large ranges, the practical exchange of matter, energy, or information between systems occurs slowly and infrequently. Even signals traveling at the speed of light require years to move between nearby stars, making communication across these distances inherently delayed. The transition from the solar system to interstellar space introduces a new understanding of scale, where separation becomes the dominant characteristic. Objects are no longer defined by their relative positions within a shared system, but by the vast distances that isolate them from one another. This isolation is not absolute, but it is significant enough to shape how structures form and how they are perceived across the universe. When individual stars are no longer treated as isolated points, but as members of a larger structure, the scale expands once again, and the context in which they exist changes completely. The sun, along with all the stars visible in the night sky, belongs to a single galaxy known as the Milky Way. This is not a small collection, but a vast gravitational system containing hundreds of billions of stars, along with gas, dust, and dark matter distributed across a structure that spans roughly 100,000 light years in diameter. The distances that once defined interstellar space now become small components within a much larger framework, and the separation between stars, while still immense, is only one layer of a more complex hierarchy. Within the Milky Way, the sun occupies a position far from the center, located about 26,000 light years away in a minor spiral arm, often referred to as the Orion Spur. This region is relatively quiet compared to the dense central bulge, where stars are packed more closely together and gravitational interactions are more frequent. The galaxy itself is not static. It rotates, with stars orbiting the center over time scales of hundreds of millions of years. One complete orbit, sometimes called a galactic year, takes the sun approximately 225 million years to complete. This introduces a temporal scale that far exceeds anything encountered at the level of planets or even individual stars. At the center of the Milky Way lies a supermassive black hole, known as Sagittarius A*, with a mass of about 4 million times that of the Sun. While this object does not dominate the galaxy in the same way the Sun dominates the solar system, it represents a focal point around which the inner regions are organized. The presence of such a massive object highlights the complexity of galactic structures, where gravitational interactions operate across vast distances and involve enormous quantities of mass, despite the immense size of the Milky Way. It is not unique or isolated. It is one galaxy among many. And even at this scale, it becomes necessary to consider larger grouping. The Milky Way is part of a collection known as the local group, which includes about 50 galaxies bound together by gravity. Among these, the Andromeda galaxy is the largest, containing roughly 1 trillion stars and spanning over 200,000 light years. It is currently moving toward the Milky Way. And in several billion years, the two galaxies are expected to merge, forming a new, larger structure. This interaction, while significant on a galactic scale, occurs over time scales so long that it does not resemble any form of collision familiar at smaller scales. The stars within each galaxy are so widely separated that direct impacts between them are extremely unlikely. Beyond the local group lies an even larger structure known as the Virgo supercluster, a vast collection of galaxy clusters and groups extending across tens of millions of light years. Within this structure, galaxies are not evenly distributed, but organized into clusters where hundreds or even thousands of galaxies are bound together. These clusters are connected through gravitational interactions, forming a network that extends across enormous distances. The Milky Way occupies only a small position within this larger system, and its significance continues to diminish as the scale increases. The Virgo supercluster itself is part of an even larger formation called Laniakea, a supercluster of superclusters that spans over 500 million light years and contains around 100 galaxies. At this level, individual galaxies become small components within a vast flow of matter, all moving under the influence of large-scale gravitational structures. The concept of a central point becomes less meaningful, as motion is determined by the distribution of mass across an extended region rather than a single dominant object. When the distribution of galaxies is mapped across the observable universe, an even more striking pattern emerges. Galaxies are not scattered randomly, but arranged along filaments and walls that form a large-scale structure often referred to as the cosmic web. Between these filaments lie vast regions known as voids, where the density of matter is extremely low. These voids can span hundreds of millions of light years, making them some of the largest structures in the universe. The result is a network in which matter is concentrated along interconnected strands, while most of the volume consists of empty space. At this scale, the concept of size becomes difficult to interpret in familiar terms. The Milky Way, which once appeared immense, is reduced to a small element within a much larger arrangement. The solar system, already insignificant at the level of stars, is no longer distinguishable within the galaxy. Earth, which once served as the reference point for all measurements, becomes effectively non-existent in any practical sense of scale. The progression from planets to stars, from stars to galaxies, and from galaxies to the cosmic web reveals a consistent pattern. As the frame of reference expands, previously dominant structures lose their relative importance. This hierarchy of scale does not eliminate structure, but it redistributes it across levels that are increasingly difficult to visualize. Each layer contains its own organization, governed by physical laws that remain consistent, yet produce vastly different outcomes, depending on the scale at which they operate. The Milky Way and the structures beyond it demonstrate that the universe is not a uniform distribution of matter, but a complex system shaped by gravity over billions of years, with patterns that extend far beyond the limits of direct observation. The exploration of scale does not only expand outward into larger and larger structures, it also moves inward, revealing that the same sense of disproportion exists in the opposite direction. Just as galaxies reduce the significance of stars and planets, the structure of matter reduces the solidity and permanence that objects appear to have at everyday scales. What seems stable and continuous on the surface is, at a deeper level, composed of components that are separated by vast amounts of empty space relative to their size. All matter on Earth, including the planet itself, is made of atoms. An atom is extremely small, with a typical diameter on the order of 1/10,000,000th of a meter. This is far below the threshold of direct perception, requiring specialized instruments to observe even indirectly. If a line of atoms were arranged side by side, it would take millions of them to span the width of a human hair. These numbers, while precise, are difficult to interpret intuitively because they operate on a scale that does not correspond to any direct human experience. The internal structure of an atom reveals an even more significant disparity. At the center lies the nucleus, composed of protons and neutrons, which contains nearly all of the atom's mass. Surrounding this nucleus are electrons, which occupy a region much larger than the nucleus itself. If the atom were scaled up to the size of a stadium, the nucleus would be comparable to a small object at the center, while the electrons would exist at distances that leave most of the volume empty. This means that the matter making up solid objects is not densely packed in the way it appears, but instead consists mostly of empty space with small regions of concentrated mass. This pattern continues at smaller scales. Protons and neutrons are themselves composed of quarks, which are fundamental particles as far as current understanding extends. These components interact through forces that operate over extremely short distances, and the structure they form is governed by principles that differ significantly from those observed at larger scales. The result is that the apparent solidity of matter is an emergent property arising from interactions between particles rather than from continuous, densely packed material. If the empty space within atoms were removed and all matter on Earth were compressed so that nuclei were in direct contact, the size of the planet would be dramatically reduced. The entire mass of Earth could fit within a volume comparable to that of a large structure, far smaller than its current diameter of approximately 700 kilometers. This demonstrates that the physical size of objects is not determined solely by the amount of matter they contain, but by how that matter is distributed across space. The concept of scale also extends into time, where a similar pattern of disparity appears. Earth formed about 5 billion years ago, while the universe itself is approximately 13.8 billion years old. This means that Earth has existed for only about 1/3 of the total history of the universe. Within that time frame, the emergence of life and the development of complex organisms occupy only a small fraction. Simple life appeared relatively early. But for most of Earth's history, it remained at a microscopic level. Complex, multicellular organisms have existed for only a few 100 million years, and human beings for an even shorter period, on the order of hundreds of thousands of years. When these intervals are compared using a compressed time scale, the difference becomes more apparent. If the entire history of Earth were represented as a single year, life would appear within the first few months. But complex life would not emerge until near the end of the year. Human existence would occupy only the final moments of the final day. Recorded history would be reduced to a brief interval at the very end of this sequence. This illustrates that, just as physical size can be misleading, duration can also be difficult to interpret without a consistent frame of reference. Looking forward, the disparity continues. The sun is expected to remain stable for several billion more years before undergoing changes that will eventually render Earth uninhabitable. On longer time scales, the universe itself will continue to evolve over trillions of years, far exceeding the current age of stars and galaxies. The existence of Earth, when placed within this broader context, represents a limited interval rather than a permanent state. These considerations reveal a consistent pattern across both space and time at every level, from subatomic particles to cosmic structures. There are differences in scale that challenge intuitive understanding. Objects that appear solid are mostly empty. Durations that seem long are brief in a larger context. And structures that seem stable are part of processes that extend far beyond immediate perception. The fragility of existence emerges not from any single factor, but from the combination of these disparities, where both size and time operate on ranges that exceed direct human experience. At the end of this progression through scale, after moving from the surface of Earth to the largest known structures in the universe, and then inward to the smallest components of matter and the longest spans of time, a consistent conclusion emerges. Earth does not occupy a central position in any measurable sense. It is one planet among many, orbiting an average star, located in a peripheral region of a typical galaxy, which itself is one among trillions in terms of size, mass, and location. There is nothing that distinguishes it as structurally significant within the larger framework of the cosmos. Yet this conclusion, taken alone, does not fully describe its role. A clearer perspective is provided by an image captured in 1990 by the Voyager 1 spacecraft as it moved toward the outer edge of the solar system. At a distance of several billion miles, it turned its camera back toward Earth and recorded what has come to be known as the pale blue dot. In that image, Earth appears as a fraction of a pixel, suspended within a beam of scattered sunlight. It is not a detailed sphere with visible continents or oceans, but a point of light so small that it is nearly indistinguishable from noise in the image. This representation is not symbolic. It is a direct consequence of distance and scale. From even a modest distance beyond the solar system, Earth ceases to be a visible world and becomes a barely detectable signal. The significance of this image lies in what it represents rather than in its visual detail. Every human who has ever lived existed on that point. Every event in recorded history, every cultural development, every scientific discovery, and every individual experience occurred within that small region of space. The scale of the universe does not diminish these events, but it places them within a context where their physical extent is extremely limited. The boundaries that define nations, the conflicts that arise between groups, and the distinctions that appear meaningful at human scales all take place on an object that becomes effectively invisible when viewed from a larger perspective. This does not imply that human activity lacks importance. Instead, it highlights the difference between physical scale and experiential significance. Earth may be small in comparison to stars and galaxies, but it contains the only known instance of life. More specifically, it contains systems capable of perception, reasoning, and reflection. The processes that give rise to these capabilities are not evident in the structure of the universe at large, and it remains uncertain how common such processes are elsewhere. As a result, the presence of life, and particularly conscious life, introduces a form of significance that is not captured by measurements of size or mass. The ability to understand and describe the universe is itself a consequence of this condition. The same matter that forms stars and planets has on Earth, organized into systems capable of observing those structures and constructing models to explain them. This creates a situation in which the universe, through the processes occurring on a small planet, becomes capable of examining its own structure. The contrast between the scale of the universe and the scale of the systems performing this analysis is one of the more notable aspects of modern scientific understanding. This perspective also introduces considerations related to responsibility. If life and consciousness are rare, then the conditions that support them may also be rare. The continuation of these conditions depends on the stability of the environment in which they exist. Changes to that environment, whether through natural processes or human activity, can alter the systems that sustain life. While the universe as a whole is not affected by such changes, the specific region in which life exists can be significantly impacted. This creates a situation in which actions taken on a local scale have consequences that are limited in extent but significant in effect. Future developments may alter the distribution of life beyond Earth. Technological advancement could allow for the expansion of human activity to other environments within the solar system or beyond. However, even in such scenarios, the scale of the universe ensures that expansion would occupy only a small fraction of the available space. The distances between stars and galaxies impose constraints that are not easily overcome, and any extension of life beyond its current location would occur gradually and unevenly. The progression from a perception of Earth as vast to an understanding of its relative scale does not eliminate its importance. Instead, it reframes that importance in terms that are not tied to size. The pale blue dot is small, but it is the location where known life exists, where complex systems have developed, and where the capacity for understanding has emerged. Within a universe that is largely empty and governed by processes that do not inherently produce such systems everywhere, this distinction remains meaningful. The relationship between scale and significance is therefore not linear. An object can be physically small while still representing a unique set of conditions. Earth size, when compared to the observable universe, approaches insignificance in measurable terms, but the processes occurring on it do not scale in the same way. The final perspective that emerges is not one of dismissal, but of context, where physical dimensions are only one aspect of a broader understanding of existence.